Okay, in this video, we're going to take a look at example 1 to get a sense of how exactly this idea of a dependent study can be done. All right, so let's take a look at the following. A shoe manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's new strength shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the strength shoes for 8 months, their vertical jump heights are measured again. So you can kind of see here we have like a before and after kind of study. The vertical jump heights in inches for each athlete are shown in the table below. So I can see here that I got athletes number 1, 2, 3, all the way down the line, but I also have their jump heights recorded before and after. So maybe I want to go ahead and do this. I want to determine the improvement in the jump heights for each of the athletes. Well, that should be pretty easy to figure out. Like if I looked at athlete number 1 here, I could ask the simple question, did they get better or worse after using the shoes? And it seems like saying they got better is a pretty obvious answer because they jumped higher after they wore the shoes. But how much higher? It seems like I could list that improvement as it was an improvement of 2, maybe say 2 inches. Person number 2 also got better. They got better by 3. Person number 3 didn't get any better, so they got a 0. Person number 4 got better by 1. Person number 5, kind of slacking there. They did worse. So they went down by 2. I'll give them a score of -2. Person number 6 went up by 2. Person number 7 went up by 5. And person number 8 went up by 3. So these would be different improvement numbers. And so if we take a look then at part B, we can see that some athletes will improve and others did not improve. But I might be asking the question, what was the average improvement? Okay, well, if I wanted to find an average improvement, I could easily go and just crunch out an average for all of these values. And I'm going to show you how to do that in one of 2 ways. So I'm going to go to the calculator here really quickly to see how I can get these numbers into the calculator. I've actually already gone ahead and typed in the original values from the lists for my before jumps and my after jumps here. And I would ask that you pause the video and try to do the same thing. So I'm going to show you a way that we can actually calculate all of these improvements very, very quickly in the calculator. So pause the video, make sure you get these entered, and then you can click play again to resume. Okay, so if we have all of our numbers entered, if we wanted to go ahead and fill in this, say, this third column with all of our improvements, that's super simple. All we have to do is either A, manually type all of these in, which is kind of annoying. So we're going to look at a formula way to do this. If I can go here, I can see that when I move my arrow keys around, I can slide this black box around on the page. I want to go up and highlight the box that's called L3. And when I'm here, what I can start to do is to type in a little formula. You'll notice down at the bottom, there's a blank space for a formula to be entered. What I want to do is I want to take my after jumps, which is L2, so I'll click second and 2, and then I want to subtract from that the numbers in list number 1. If I do this, notice it automatically does that subtraction, and they're the exact same numbers from the box above. So that's a really quick way that you can get those numbers without a whole lot of work. Because it's kind of annoying. If you imagine I had 80 athletes, I don't want to do each of those subtractions by hand. So when I look at what part B is asking, it says, what was the average improvement and what was the standard deviation of the improvements? Well, I know how to get that information. I could do a 1-var stats with the numbers from list number 3. And if I was to do this, I could see that my average improvement, which I'm actually going to change here to a symbol D bar. Instead of X bar, I'm going to use a D bar because I had differences or improvements. And it seems like the improvement was about 1.5 or 1.75 inches. And it looks like the standard deviation, I'm going to give it a subscript here of a D because it's the standard deviation for the differences, was about 2.1213 inches. And I should write that with a squiggly equal sign. Okay, so again, I can start to see that not all the improvements are the same. They vary. The average improvement is about 1.75 inches. Don't be surprised if people go up or down by the standard deviation amount. The question that we're going to pose in this section is, what hypotheses could we form to explain why we got this average improvement in the way that we did? So here's one hypothesis, and it's our age 0. What I could say here is something kind of boring. I could say like the shoes don't affect vertical jump height and the average for all people will be 0, right? Like this was an average of 1.75, but you only looked at 8 people. By the time you look at all the people, these shoes will have essentially 0 effect, right? So essentially here we're claiming that the average for all the differences, this is our mu d, we're going to claim that, yeah, that's just going to be nothing. That's an option, right? Like we kind of got lucky here. But if I look at what H1 would say, that's the more interesting hypothesis. It would say the shoes do affect vertical jump height, and the average improvement for all people will be more than 0, right? That if these things do better, I should expect positive numbers coming back, kind of like what we saw here with our D bar. So here symbolically we have another hypothesis. So I'm writing these out in words here so we can try to make sure that we understand how do these hypotheses relate to the scenario and what do they look like symbolically. Now if we take a look at part D, we can see one other thing, is that realistically here, this is a test that's really going to deal with 2 hypotheses about a single average. So here's the best part. We actually have a previous test that can help us determine which of these hypotheses is best. And in this case, you might be able to look back at the formula sheet to figure out what calculator test could I run that only tests for a single average. I could actually go back to section 7.2 and we could run a t-test. So this is really, really great. The best part about this section is that we only have to introduce or use ideas from previous sections. Okay. So I have down here at the bottom just some reminders of some of the things that we did. At the very bottom, I have these calculator commands, how we actually went through and created that L3 column. And otherwise on the side, I have kind of all these symbols listed out that we've used. If D stands for the differences between a pair of data, ND is the number of the data pairs that we have. D bar was our sample average. SD was our sample standard deviation. And mu D was the hypothesized mean for all the differences in the population. So when we go ahead and run this test, we're going to see that we don't actually have blue or black hypotheses and green hypotheses. We're kind of just back to single hypotheses, where we're going to have mu D is either equal to a number or smaller or greater or not equal to a number. We're going to be able to write down all of our stuff and plug things into a calculator. We're going to be able to get a t-distribution back. We're going to see that we can draw our picture out, reach a conclusion, all using a t-test. So this is going to be really great news. And in the next video, we'll see exactly how we actually do this in example number 1 continued.